Our last section for the equilibrium unit is going to be returning to free energy, that's delta G, and looking at how that relates to equilibrium. Right, so I have three different graphs here, and we have sort of three different sets of circumstances if you have a reaction where you have one gas being converted to a different gas. So this is just a hypothetical simple reaction where we have gas A being converted to gas B. So if the equilibrium constant is 1, that's where I'm going to start actually, which is part C here, then that would mean there's an equal concentration of A and B at equilibrium. So our K would be 1, and it means that the delta G for that reaction is going to be 0. Neither the left side or the right side is more favored. They're equal. Okay. If, however, A is more favored, then we're going to have a K that is less than 1 because the reaction is going to be more favored toward the left. We're going to have more reactants, and more reactants would indicate that the reactants are more more stable, more energetically stable, and that would mean a delta G that is positive because that reaction is not going to go very far toward the products. Okay, and then the last one, which is B here on our diagram, is if B is more stable, gas B, and if that's the case, then our reaction is going to shift more toward the products, and so at equilibrium, our K is going to be bigger than 1, all right, and that would be a reaction that's going to be spontaneous in the forward direction, which would indicate a negative delta G, because remember, if it was thermodynamically favored, we said we had a negative delta G, and if it was unfavored, we had a positive delta G. So here we have a reaction that goes both directions. So if the reactants are favored, it would be positive delta G, and if the products are favored, it would be negative delta G, and if they're equally favored, or K is 1, then we're going to get a delta G of 0. So this slide just sums up what I just said to you. So the equation that actually relates these two things is here. It's delta G naught of the reaction is equal to negative RT and the natural log of K, which is the equilibrium constant. So if you were to plug in these different values for K, which I just showed you on the previous slide with the graphs, you get the delta G's that we just talked about that correspond to them. So if K is greater than 1, delta G is less than 0. If K is less than 1, then delta G is greater than 0, and if K is 1, delta G is equal to 0, because the natural log of 1 is 0. Okay? So now we can use this equation, and along with what we learned back in the thermodynamics unit, to calculate our equilibrium constant this way. So if we have the equation here, N2O4 goes to 2NO2, and we have the delta G of formations for each of the reactant and the product. You can go ahead and calculate a delta G. So if you remember, delta G of a reaction is going to be equal to the delta G of formation of the products minus the delta G of formation of the reactants. So here we have 2 times the delta G of formation for NO2, which is 51.3, minus 99.8, which is the delta G of formation for N2O4. Right, so that gives us a delta G for this reaction of 2.8 kilojoules. And then if we plug that into the equation we just got, we have the delta G of reaction equals minus RT ln K. So now we plug in the R, which is 8.314, and this is a new R, but it's also on your equation sheet, and the units for that are joules per mole Kelvin, and we can plug in the temperature as 298 Kelvin. And then our delta G has to be in joules per mole now because of the units of R. So that's going to be 2.8 times 10 to the third joules per mole, or 28,000. Okay, so we solve that. That would give us K is equal to e to the minus 1.13, okay, because the inverse operation for the natural log is e to the x, right? And then we solve for K and we get 0.32. And you can see here that we have a K that's less than 1, which is consistent with a delta G that's positive. So this makes sense based on what we talked about qualitatively in the beginning. Right, and then the final thing I want to talk about is just that there's the temperature dependence of the equilibrium constant. So what we've talked about with Le Chatelier's principle is that if the reaction is endothermic, increasing the temperature, if heat is acting as a reactant in an endothermic reaction, then increasing the temperature would shift the reaction to the right, and decreasing it would shift it to the left. And if it's exothermic, the opposite is true. Okay, so that's just one way to think about it, but this is actually because the equilibrium constant itself changes with temperature. And so we're not going to calculate them, but I just wanted to point that out to you, and we have the two equations. We could combine them if we wanted to and get minus RT ln K equal to delta H of a reaction minus T delta S of the reaction. So all of those quantities are temperature dependent, and so that's why in equilibrium problems a lot of times they'll give you the concentrations and stuff at a particular temperature. You don't usually have to use the temperature in your calculation, but this is the reason why, because the equilibrium constant changes if you change the temperature.